All right, let's look at the logistic equations. All right, logistic equation is a model that is a little bit more realistic than exponential population model. All right, it says this. The rate of change of population with respect to time is proportional to the product between a population itself and m minus population. Right here, m is some sort of capacity called the carrying capacity. Right? And initial conditions, let's say P of 0 is P0, right? Looking at this differential equation, we can kind of predict what the population is going to behave based on the initial population. Right? For example, right, let's look at the population starting from smaller than m, right? So let's say here, right? Then if you look at the rate of change of population, k is a positive constant, and population is going to be, of course, positive, and m minus p is going to be also positive. So you're going to have a positive slope. That means that it's increasing. As population gets closer to m, the rate of change is gonna die down, gets closer to 0, so it's gonna kind of flatten out. So the population is gonna behave like this. So initially it's gonna grow kind of fast, but as it gets closer to m, it's gonna kind of flattens out like that. All right. But if the initial population is greater than carrying capacity, let's say you start from here, right, then you can see that the p is positive. M minus p is going to be now negative. So you're going to have a negative slope, which means that the population is going to go down. But as before, as the population gets closer to m, then the curve is going to kind of flatten out. So the population is, kind of gets closer to m. And if you look at the limit of this population p of t, as say t approaches infinity, is going to be this carrying capacity. And also carrying capacity, because of this, it's also called the limiting population, right? So it has a fairly realistic a model for population because of the food restriction or the space restriction. The population cannot grow, larger and larger. It has to kind of stop somewhere. So that's what the carrying capacity is. All right, so next, let's try to see if we can solve this differential equation using the technique we already have. All right, so let's start with this differential equation. All right, dp over dt is equal to, all right, k times k is a constant, population p times carrying capacity minus p. Right, so first step, since this is a separable equation, I'm going to divide both sides by p times m minus p. Right, so you're going to end up getting 1 over p times m minus p. Right, so you have dp over dt. Is equal to, just going to be k's left over, right? To make our lives easier, I'm going to actually multiply both sides by m as well. So you have, you'll see why I'm doing this. So here's m, and I'm going to put the km here. All right. Then once you've done that, we want to take the antiderivative of both sides. So you're going to take the antiderivative here with respect to t. So we're going to have dt here, integral sign with dt there. Right? Then we can cancel dt here, dt there, right? So in order to evaluate this integral, I'm going to do partial fractions, right? I'm going to skip the step of finding the constant, but it's going to look like this. It's going to be 1 over p, right? Plus 1 over m minus p, right? We still have to integrate it, right? With respect to p on this side, and this side, I'm going to go ahead and do it. So it's going to be k m is just a number, so it's a times t plus some constant. I'm going to call it c1. All right. And I'm going to do a little bit of adjustment since I know to find the antiderivative here, because derivative of this guy with respect to p would be -1. So I would like to have a negative sign here. So I'll put the negative sign, and I'll turn that into a negative, right? So let's evaluate that. So this is going to, antiderivative is going to be natural log of absolute value of p, right, minus absolute value of a natural log of absolute value of m minus p, right? And this is equal to kmt plus some constant c1, right? So I'm going to put those guys together using log property. So this is going to be natural log of absolute value of p over m minus p, right? Because subtraction outside becomes division inside, and the right hand side is still be the same. So you have a kmt plus c1, all right? So in order to get rid of a natural log, I'm going to raise e to the both sides of the equation, right? And that way we can cancel. Here's a natural log and an exponential function. They're inverses of each other, so you can cancel each other out. And right hand side, we can actually write it as e to the kmt, and then times, I'm going to put e to the c1. Right, so we have that. Then since this is, I want to get rid of the absolute value sign, so I'm going to get rid of the absolute value sign so that I can just put plus or minus here. All right, then I'm going to call this constant, the plus or minus e to the c1, I'm going to call it c. All right, so this is what you get. So you're going to have p over m minus p is equal to c times e to the kmt. Right, so we got that. Right, so before we go any further, I'm going to actually use this initial value condition here so that we can find this c. Right, so I'm going to plug in 0 here. So p of 0 is p0. Right, so I'm just plugging in t equals 0. Then you're going to have m is just a constant that stays as m. So p of 0 is p0. And this is equal to, right, so e to the 0th power is going to be 1. So you're just going to end up with c. Right, so you have this expression for c. Right, so let's keep this guy in mind. All right, so let's keep going. So we're looking for p, so we just need to solve for p. All right, so I'm going to multiply through by m minus p so that we have a p here, right? Then we're going to have mc e to the kmt, and a minus, right? So you're going to have a c e to the, or actually maybe I should put the p first, right? So it's actually c e to the kmt times p, right? That looks actually better, right? So I'm going to solve for p, so I'm going to add c e to the kmtp to both sides. So you're going to get, from here, you get 1. From here, you get plus c e to the kmt p is equal to mc e to the kmt. Alright, then we can just divide through by quantity 1 plus c e to the kmt, and you end up with p is equal to, right? So we have a mc e to the kmt over 1 plus c e to the kmt. Alright, so since there are 2 e to the kmt, I'm going to multiply, or actually divide, multiply by e to the negative kmt, which is just a reciprocal, right, on top and the bottom. Alright, then you're going to get this. Alright, so you're going to have mc over, right? I'm going to actually 1 times e to the negative kmt here. So it's going to be e to the negative kmt, right? So it's going to be plus, right? That's cancel out. You're just going to get c, right? So next step would be, since we have a c, and which is here, so we can plug it in here and plug the same thing in here, right? So you're going to end up getting, right? So you have a m times p0 over m minus p0 over p0 over m minus p0 plus e to the negative kmt, right? And the last step, this looks very horrible, so I'm going to multiply top and bottom by m minus p0, right? M minus p0, right? So what you end up getting is going to be, so I'm going to just say, therefore, p population can be found, right? So m minus p0 cancel out, so you're going to get m p0 divided by, right, on the bottom, so that cancel out, so you have a p0 here, plus, right, so you have to multiply by m minus p e to the negative kmt, right? So that is the population function that we're looking for from the logistic equation, right? And you can see the limiting population from this formula too. So for example here, if you take the limit, let's take the limit, maybe right here. So limit of this function we just found, mp0 over p0 plus m minus p0 e to the negative kmt as t approaches infinity, right? And if you look at the expression e to the negative kmt, because of its negative sign, you're going to have e to the negative infinity, and this guy is going to go to 0, right? So basically this cancels out, and the p0 cancel out. So what's left is going to be simply m. And you can see that this is a limiting population there. All right. So this is logistic equation, and the differential equation, then the initial value. Then the population function actually can be written as mp0 over p0 plus m minus p times e to the negative kmt. All right, that's it. I hope that this was clear.